Hello friends, in Chemical Kinetics, in this video I am going to discuss about the integrated rate equations and half-life period for zero and first order reactions and meaning of pseudo first order reaction. Let us see one by one. In the previous videos we have discussed about the differential rate equation, but these equations have some limitations. Actually, this is the form of differential rate equation. Clear? In this case, concentration dependence of rate is called differential rate equation. It is not always convenient to determine the instantaneous rate. This term minus dr by dt, this representing the instantaneous rate, and it is not convenient all the time. Why? Because it is measured by determination of slope of the tangent at point t in the concentration versus time plot. This makes it difficult to determine the rate law and hence the order of the reaction. In order to avoid this difficulty, we can integrate the differential rate equation to give a relation between directly measured experimental data, that is concentrations at different times and a rate constant. Now just see, first we'll discuss about the integrated rate equation for zero order reaction. What is the meaning of this zero order reaction? It is rate of the reaction is proportional to zero power of the concentration of reactants. Then this is called zero order reaction. If we consider this general equation, reactants are converting into products, and for this we can write the differential rate equation like this. Rate is equal to minus dr by dt is equal to k r power 0. This 0 represents the zero order reaction, and this term r power 0, this becomes equal to 1. Clear? Then this equation rate is equal to minus dr by dt is equal to k. This can be written like this: dr is equal to minus k dt. If we integrate this equation both the sides, we will get this one: r is equal to minus kt plus I, where I is the constant of integration. Clear? If you can learn this, it is better. Clear? If you don't know the integration, it is very easy to by heart this conversion. Now, how can we find out the value of I, constant of integration? When time t is equal to 0, then we can say concentration of the reactant R is equal to R naught. Clear? Where R naught is the initial concentration of the reactant. If we put this value into this equation, R naught is equal to minus K. T is equal to 0 plus I, then we will get R naught is equal to I. And if we put the value of I into this equation, then we will get this: R is equal to minus KT plus R naught. Now again, if we rearrange this equation, then we will get, okay, first of all, before rearranging, just compare this equation with the equation of straight line y is equal to mx plus c. Clear? If we plot a graph between R and T, R on that y-axis and T on x-axis, then we will get this straight line, and in this straight line its slope is equal to minus k. The slope is equal to minus k, or we can say k is equal to minus slope, and this is the intercept from this to this. This is intercept, and this is equal to R naught. Clear? That's why this is the graph for the integrated rate equation for zero order reaction. Now again, rearrange this to this. We can say this is KT is equal to R naught minus R, and then we can say K is equal to R naught minus R by T. You have to remember this equation. This is useful. Zero order reactions are relatively uncommon, but they occur under some special conditions, like some enzyme catalyzed reactions and reactions which occur on metal surface are few examples of zero order reactions. Now just see, decomposition of gaseous ammonia on a hot platinum surface is zero order reaction at a high pressure. See this, 2NH3. In these conditions, this will convert into N2 plus 3H2, and if we write the rate equation for this, rate is equal to K. This is NH3 power 0, and that is equal to K. Another example is thermal decomposition of HI on gold surface is the another example of zero order reaction. Now next come to the integrated rate equation for first order reaction. What is first order reaction? The rate of reaction is proportional to the first power of the concentration of reactant R. Again, consider one hypothetical equation. Then we can write the rate expression for this. Rate is equal to minus dr by dt is equal to kr. Again, if you just rearrange it, you can write that is dr by r. dr by r, this is equal to minus k dt. I think there is no problem in this case. Now again, if we integrate this equation on both the sides, then we will get this is ln. ln is the natural log. R is equal to minus kt plus I. Again, I is the constant of integration. Again, if you find out the value of I, we can assume that when t is equal to 0, R is equal to the R naught, that is initial concentration. Put the value, then we can find out this I is equal to ln R naught. If we put this value of I into this equation, then we will get ln R is equal to minus kt plus ln R naught. Okay. Now again see this equation. Now according to this equation, again this if we compare, this is the equation of straight line. Y is equal to mx plus c. It means if we plot a graph between ln R against t, we get a straight line like this. This is ln R on the y-axis, t is on x-axis, and this is the intercept. This intercept is equal to ln R naught, and the slope of this equation is equal to minus k, or we can say k is equal to minus slope. Clear? Then again, this equation can be converted or can be written like this. It is ln R divided by R naught is equal to minus kt. Clear? Then again, if we take the anti-log of both the sides, if this equation, if we take the anti-log of both the sides, then we will get this. R is equal to R naught e raised to the power minus kt. Clear? And again, this equation can be written like this. If you just reverse it. Now we are taking ln R naught by R, then this minus sign will convert into plus, and that is equal to kt. This is again y is equal to mx. Y is equal to mx, where that is intercept is equal to 0. Intercept is equal to 0. If you plot the graph between ln R naught by R, this side on the y-axis, and time on the x-axis, then we will get the one straight line passing through the origin. Okay, and in this case, this slope is equal to k. Both the graphs for first order reaction. Remember it. Now again come to that same equation we have taken already. ln is equal to R naught by R is equal to kt. Just rearrange. We can say k is equal to 1 by t ln R naught by R. Okay. Then in this case, ln is a natural logarithm. If ln is replaced by the log base of 10, then this is multiplied by 2.303. That's why we are having k is equal to 2.303 divided by t log R naught divided by R. Again, this formula is important. You have to remember it. Okay. Now again, from this equation, that is, this can be written like this. ln R naught by R is equal to, this is kt 2.303. Again, this is equal to y is equal to mx. Y is equal to mx, where intercept is equal to 0. If you plot a graph between log R naught by R on the y-axis and time on the x-axis, then we will get the one straight line passing through the origin. And in this case, again, slope is equal to k by 2.303. Okay. Now, in this case, actually this R naught is the initial concentration and R is the concentration after time t. But if we know that at time t1 concentration is R1 and at time t2 concentration is R2, then this can be written, that is this one can be written like this. K is equal to 2.303 T2 minus T1 log R1 by R2. Clear? Now see examples of first order reaction. Hydrogenation of ethene is an example of the first order reaction. Hydrogenation means addition of hydrogen, like C2H4 plus H2 converting into C2H6. Rate is equal to KC2H4. All natural and artificial radioactive decay of unstable nuclei takes place by first order kinetics. Now what is this radioactive decay? I think in the lower class here you discussed what is the meaning of radioactivity and radioactive substances. Actually there are some substances which emit the invisible radiation alpha, beta and gamma. These are the radioactive substances. Okay, and this may be natural and this may be artificial. All natural and artificial radioactive disintegration or radioactive decay are the first order kinetics, first order reaction. Now see one example. This is Ra, radium. This is 88 is the atomic number and 226 is its mass number. When it emits the one alpha particle, what is alpha particle? This is helium nucleus, that is 2He4. This is alpha particle. Then after emitting this helium, it convert into the radon, that is 86,222. That is the mass number. Then for this we can write this rate is equal to K concentration of Ra. Okay. Another example is decomposition of N2O5 and N2 are some more example of first order reaction. Now first order reaction in gas phase. Okay. Again we take the one example. In this case all the reactants and products are in the gaseous phase. Again if we assume at initial when time is equal to 0, the pressure of the reactant is P1 atmosphere. Then naturally pressure of products will be 0 and 0. And if you assume that X atmospheric pressure is decreases for the reactant, then at time T, the pressure of the reactant becomes P1 minus X and B becomes X atmosphere and C becomes X atmosphere, because according to the stoichiometric equations, when it's 1 mole is decomposed, its 1 mole is formed and its 1 mole is also formed. Then we can say what is the total pressure at time T. This is the sum of this and this. That's why P1 minus X plus X plus X is equal to P1 plus X. And from this we can find out the value of X. X is equal to Pt minus P1. Now if Pa is the pressure of A at time T, then we can say Pa is equal to P1 minus X. Again remember, P1 is the initial pressure of reactant and Pa is the pressure of reactant at time T. Then again put the value of X in this case, then we will get this Pa is equal to 2P1 minus Pt. And again if we apply the integrated rate equation for first order reaction, that is K is equal to 2.303 divided by T log. Now this is a gaseous equation, that's why we will put this the initial pressure and this is the pressure after time T. Now in this case this Pa is equal to 2P1 minus Pt. So this formula is important for gaseous reactions. Now next, half-life of a reaction. Half-life. Again, I think you can understand what the meaning of this half-life. Half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. This is represented as T-half. T-half for zero order reaction. This is the integrated rate equation for zero order reaction. This is integrated rate equation. Now when T is equal to T-half, then we can say this R, that is concentration R, this R is equal to half of initial concentration. Okay, now put the value of this. We can say K is equal to T becomes T-half and this R becomes half of R naught. If you solve it, then we'll get T-half is equal to R naught divided by 2K. Again you have to remember this one. Clear? We can say from this formula, T-half for zero order reaction is directly proportional to initial concentration of the reactants and inversely proportional to the rate constant. Clear? Now see, T half for first order reaction. Now this is the integrated rate equation for first order reaction. When T is equal to T half, then we can say this is concentration of reactant becomes half of the initial concentration. Clear? Then again if we put T is equal to T half and this is concentration of R is half of R naught, then we will get this. K is equal to 2.303 T half log R naught divided by half of R naught. If we solve this, R naught is cancelled by R naught and then we'll get the log 2. 2.303 divided by T half log 2 and value of log 2 is 0.301. If you multiply this, we will get this one. T half is equal to 0.693 K. Again, remember this relationship. It is important for the numerical point of view. Now again, if you see this, for first order reaction, half-life period is constant because it is not depend on the concentration. In this formula, there is a no concentration term. That's why we can say it is independent of the initial concentration of the reacting species. You can see if we start from the 100 molecule, so 100 to 50 molecules, suppose it required the 10 minutes. Then again 50 to 25 molecules, again it required the 10 minutes. And from 25 to 12.5, again it required the 10 minutes. That's why T half for the first order reaction is independent of the initial concentration. Now, pseudo first order reaction. Pseudo first order reaction. Consider one chemical reaction between two substances when one reactant is present in large excess. Clear? This is the one. Hydrolysis of ester. CH3CO, C2H5 plus H2O, CH3COH and C2H5OH in the acidic medium. If we are taking the initial moles of ester is 0.01 mole and this is a solvent and this is in excess 10 mole. Then initially this is 0 and this is 0. Then after time t, if we say that it's completely hydrolyzed. It means its mole remains 0. Then from this is 9.9 mole. When this is 0.01, this is again 0.01. This will again 0.01 reduce, and this is 0.01 mole, and this is also 0.01. Actually, then when this is 10 minus 0.01, then this will equal to, this is 9.99 mole. Now see, this is the negligible change in this case. So that's why we can say the concentration of water does not get altered much during the course of the reaction. That's why rate of reaction can be written as a rate is equal to, this is K days concentration of ester, concentration of H2O, but this H2O can be taken as constant. Okay, that's why we can say this is rate is equal to K CH3CO C2H5, where K is K dash H2O, and the reaction behave as a first order reaction. This represents the first order reaction, rate expression for first order reaction. Such reactions are called pseudo first order reaction. How can we define? Actually, reactions which are seem to be of higher order. Yes, like this is seem to be second order, but actually it follow the first order kinetics. These reactions are known as pseudo first order reaction. Take one more example, that is inversion of cane sugar. That is, cane sugar means sucrose. C12H22O11 plus H2O, C6. It gives the one molecule of glucose and one molecule of fructose. Both are the same formula. And for this, if we write the rate expression, rate is equal to K concentration of cane sugar or sucrose. Clear? Thank you.